So now we've come to looking at the Schrödinger equation. So previously we've seen that sound waves and waves on a string can be described by equations that we derived from Newton's laws of motion. Similarly, you've seen that for electromagnetic waves, they can be described by equations derived from Maxwell's equations. Well, Schrödinger's equation is the equivalent for matter waves. It was first proposed by Erwin Schrödinger in 1926. So for the case where we're considering a matter wave travelling in the x direction in some potential described by u of x, we can write down Schrödinger's equation as d squared psi dx squared plus 8 pi squared m over h squared times e minus u of x times psi is equal to 0. The E in this equation stands for the total mechanical energy. So here we're considering the non-relativistic case, so we don't include any of the mass energy terms. Now, this equation cannot be derived. It's a basic principle, just like Newton's laws and Maxwell's equations were basic principles. So to try and wrap our heads around it, let's now look at a really simple situation where we can apply Schrödinger's equation.
Okay, so we can write Schrödinger's equation as d squared psi dx squared, so the second derivative of psi with respect to x, plus 8 pi squared m over h squared times e minus u of x psi is equal to 0. Now, physically, E is the total mechanical energy, and ux is the potential. So let's consider the case where the potential is constant. It could even be 0. And we know that the total mechanical energy minus the potential energy gives us the kinetic energy, which is given by a half mv squared. Now, a half mv squared, we can write this as a half mv all squared on m. So this is equal to a half p squared on m. And we've done this because we know that the momentum can be expressed in terms of the wavelength as h over lambda. So we can write this as 1 over 2m h over lambda squared. Okay, now what we're going to want to bring in, you'll see why in a minute, is the wave number again. So remember, the wave number k is equal to 2 pi over lambda. So we can replace this lambda here. This tells us that lambda is equal to 2 pi on k. So let's replace this lambda with 2 pi on k. So this is equal to 1 over 2m times h over 2 pi and a k there, and that's squared. So we can expand this bracket and we have h squared k squared over, this is 4 pi squared times 2, so this will be 8 pi squared m. Okay, so that's equal to E minus U, which is this term here. So going back to Schrödinger's equation, we can now write this as d squared psi dx squared plus 8 pi squared m over h squared times this, which is h squared k squared over 8 pi squared m psi is equal to 0. And now you can probably see why we introduced this wave number here, because now we've got a whole lot of terms which are going to cancel out really nicely. So this cancels this h squared cancels. So now we have the nice simple equation d squared psi dx squared plus k squared psi is equal to 0. So what we want to do now is find a psi that is a solution to this equation here. So it was a long time ago, I know, but when we approached a similar situation where we were looking at sound waves, or waves on a string, we just suggested an equation and showed that it satisfied this. So let's take a similar approach here. I shall tell you that a solution is psi is equal to a e to the ikx plus b e to the minus ikx. And what we'll do is we'll show that this is a solution. Okay, so to do that, we're going to need to get the second derivative for this part here. So we've got d psi dx, taking the derivative of this, we have a times I k e to the ikx plus b times minus ik times e to the minus ikx. And then what we need to do is take the second derivative, d squared psi dx squared. And so that'll be a times, we need to times it by ik again. So that's ik squared e to the ikx plus b. And this time we times it by minus ik again. Minus ik squared e to the minus ikx. So this is equal to a, now I squared, that's minus 1. So this will be minus a k squared e to the ikx. Now minus I all squared, that's the same as I squared, so that's minus again. So this is minus b k squared e to the minus ikx. So now we're going to substitute in here. So we have minus a k squared e to the ikx minus b k squared e to the minus ikx. That's this part, plus k squared times psi, and psi is this, so that's a e to the ikx plus b e to the ikx. Okay, so we've just got a k squared here. You can see this term here is going to cancel this term, and this term is going to cancel out this term. So this is indeed equal to 0. So it does satisfy the equation. So we've shown a solution now to our Schrödinger equation. So this is our solution to the Schrödinger equation given that u is constant.